Welcome everyone. In this lesson, we're going to be looking at optimization. So optimization means trying to locate the maximum or the minimum value for a function. And this is topics that we've seen before, but what we're going to be looking at now is optimization subject to a constraint. And the first type of constraint that we're going to look at is what we see in example 1. So let's just read through this example and we'll talk a little bit about the constraint. So we want to find the minimum value for this function right here, and we're given this nice explicit formula for our function. But that's not it. We also have this condition, this constraint, this inequality that puts some restriction on where we can look. And so this is, we'll call this an inequality constraint. So it puts some restriction on where we can look. We can only look, in this case, at the x values that are greater than or equal to 0. All right, so let's actually see how we're going to do this. And it's going to start off like what we've seen before. We're going to locate the critical numbers, and then we're going to test them to see what's going on at each of the critical numbers. And so that's going to be the first thing. Step 1, get the critical numbers of our function f of x. And the way we do this is where we find the first derivative and then set the first derivative equal to 0 and solve for x. So we're going to calculate our first derivative, and then once we have that, we're going to set our first derivative equal to 0 and solve that for x. All right. Our usual steps. So let's try it out. Let's get our first derivative. Let's calculate it. So when we differentiate, we get 6x squared minus 30x plus 24. And then as usual, as soon as we have our first derivative, let's see if this thing factors. And the kind of one thing I notice is that each term here has a factor of 6. So I'm going to start by factoring out that 6, just to make all the other numbers maybe a little bit smaller, which will make trying to factor the rest of the thing a little bit easier. So when I factor out the 6, I'm going to have x squared minus 5x plus 4 left over. And then now the numbers are a little bit smaller. It's a little bit easier to factor. And I see that this does actually factor into x minus 1 times x minus 4. And then I still have that 6 there as well. All right, so it factors nicely. Then once we have our first derivative all calculated and factored, we can set the factored version equal to 0. And then we want to continue solving for x. And we're only going to get a solution for x from the terms, the factors that actually have an x there. So this 6, that's not going to give us a solution. We're only going to get a solution from here and from here. So if we set this factor equal to 0, we're going to get x equal to 1. And then if we set this factor equal to 0, we're going to get x equal to 4. All right, so we get two critical numbers here. And so once we have our critical numbers, then the next thing is we want to actually test them. But before we do that, we want to keep this constraint in mind. And so any critical numbers that we find, we're only going to use the ones that satisfy this condition. And it turns out both of them satisfy, in this case, both of them satisfy that condition. X equals 1, well, that's bigger than 0, and x equals 4, that's bigger than 0. So both of these meet that extra condition or that constraint. If, for instance, we had also found maybe we found like -1 as a critical number. So suppose we had -1 as a critical number. Well, that doesn't meet the constraint, and so we wouldn't use it. So when you have your critical numbers, you want to check. Well, let's put it this way. You only want to use the ones that meet the constraint. So we're only going to use the ones that satisfy the constraint. And in this case, both of them do, so we're good. All right. So now we go, once we've done all this, we're going to test them. So test our critical numbers. And when we do this, we have two options. We have our first derivative test and our second derivative test. So we can do either one. So it really depends on which one you want to do. But we're going to try also sketching the graph. And so it's going to help to know the intervals of increase, to get a rough sketch of what our function is doing. And it's also going to be helpful to have those intervals of increase decrease to see what's going on at the endpoint here. So we're going to talk more about that endpoint x equals 0. So for this, we're going to use the first derivative test. And that means we're going to do a sign chart for f prime. All right, so when we do our sign chart for f prime, we're going to draw the x-axis. There it is. And when we do this, we also want to keep in mind our inequality here. So we're not going to draw all of the x-axis. We're going to start our section of the x-axis at x equals 0 here. So we're also going to plot x equals 0. And that's going to be an endpoint. So we're kind of keeping in mind again that this inequality constraint is here. All right, so once we have that, we'll plot our critical numbers, x equals 1, and then x equals 4. And then this gives us kind of, again, it splits up the x-axis now into 3 intervals. So we have our endpoint at 0, and then we're going to 1. And then we're going from 1 to 4, and then from 4 to infinity. And because this is a equal sign, there's an equal sign here, I'm using a closed bracket at that endpoint x equals 0. All right, so now we want to do our sign chart for f prime. And I can pick, when I do this, I want to use all the factors of f prime. So I'm going to write a row for 6, for x minus 1, and then for x minus 4. And I want to figure out, well, what is the sign of each of these factors for each of these factors on each of these intervals here. So let's start with this interval from, well, let's first start with the easy one, 6. 6 is always positive. So we could go right across the row there and mark all those as positive. Then let's look at x minus 1, and we want to test this factor. Now for this first interval, we want to pick some number that's in this interval here. And we can use 0 because it's not a critical number. So if I were to pick 0 and plug it in, I would get -1. So on this first interval, it's negative. Then if I were to go to the next interval, pick a test number, so maybe like 2, plug it in, I get 2 minus 1, positive. And then go to the last interval, bigger than 4, I could pick 5, plug that in, I get 5 minus 1, positive. And then we do the same thing for the other factor, x minus 4. So again, I could start with 0, plug it in. I get 0 minus 4, which is negative. Then I could go to the next interval, pick something like maybe 2. Plug 2 into our x minus 4 factor. I get negative 2, so negative. And then finally, pick something bigger than 4. So maybe, again, something like 5. 5 minus 4 is positive. And so since I used all the factors here for f prime, multiplying all these together is going to tell me what f prime is doing, and then that'll ultimately tell me what the original function is doing in terms of increase and decrease. So let's see. For this first interval here, if I multiply all these factors together, I'm going to have a double negative, so that's going to become positive. And then positive times a double negative is going to be positive. So that means f prime is positive on that first interval, which means our original function is going to be increasing on that first interval. Then we go to the next interval in between 1 and 4, and what we have here is a positive term times a negative term. So overall the result is going to be negative, and if f prime is negative, that means our original function is going to be decreasing. And then finally, for the last interval, everything is positive, so that means f prime is going to be positive, which means the original function there is increasing. And so with these intervals of increase-decrease, we can see, if we kind of do a rough sketch of what our function is going to look like, it's going to be increasing, and then it's going to flatten out, and then decrease, and then flatten out, and then increase some more. And then we have an endpoint there at x equals 0. And so the first derivative test, if we kind of sketch in what our graph looks like, the first derivative test says not only does it look like we're going to have a max here when we switch from increasing to decreasing, but we actually do. And same thing here. It looks like we're going to have a low point, and we actually do have a local min. So what we're seeing is that there is a local min at x equals 4 and a local max at x equals 1. So we're able to classify our critical numbers by knowing the intervals of increase-decrease here using that first derivative test. Okay. So far this is all pretty standard. Now we want to sketch the graph. And we're going to keep in mind this inequality here, this inequality constraint. And so what we're going to do is we're going to figure out what the local max point is. And we're going to figure out what the local min point is. And then we're also going to figure out the endpoints, any endpoints. So our local max point, we found one local max, and it happens at x equals 1. So what's the actual y-coordinate for that point? Well, the way we can figure out the y-coordinate is by plugging into the original function. So we're going to plug 1 into the original function. So what do we get? Let's pop back up to the original function. Here it is. We plug 1 in for x, and we're going to get 2 minus 15 plus 24 plus 19. So when we calculate that, we're going to get 30. So we're using the original function here to find our y-coordinate. So that's important to keep in mind. Whenever we want the y-coordinate, we're using the original function. All right, so what about the minimum point? We know this happens at x equals 4. So again, we want the y-coordinate for this point. So we're going to plug 4 into the original function. And if we do the arithmetic, we end up with 3 as the y-coordinate. So we can plot these points on the graph, on the xy plane here. So we found that at x equals 1, this is our maximum point, our local max, and it was 1, 30. And then at 4, we found our minimum point, so that was 4, 3. And then what happens with this constraint, this inequality constraint, is it's possible if there's an endpoint that we could have a max or a min at that endpoint as well. So we also need to keep in mind what's going on at x equals 0. And that's what we're going to do. So there's an endpoint at x equals 0. And so again, we want the y-coordinate just to see where this is. We plug 0 into the original function. So let's go see what we're going to get. So we go back up to our original function. Here it is. Plug 0 in. We get 0, minus 0, plus 0, and then 19. So f of 0 is equal to 19 in this case. All right, so let's also plot that point on our graph. So at 0, we're right there at 19. All right. And so let's sketch the graph just to see what's going on. And let's use our intervals of increase, decrease to kind of help guide the way. And so what we found, if we go back up, is that we had 3 intervals. On the first interval, we're increasing. On the second interval, we're decreasing. And then we switch back to increasing. So let's just translate that down to our x-axis down here. So we're increasing, then we're decreasing, and then we're increasing after that. So increase, decrease, and then back to increasing. And so how this would look, just a rough sketch. We could, if we wanted to make this better, we could also look at the second derivative and the intervals of concavity. But just to get a rough picture of what this thing looks like, our graph is going to increase from this endpoint, then it's going to flatten out at our local max, and then it's going to decrease. And maybe we'll make this a little more even. And then again, it's going to flatten out there at our local min. And then from here, it's going to increase again. And try that again. Something like that. And it's going to keep going up like this. All right, so looking at this sketch, we can see that if we compare the endpoint to our local min is actually the smallest point on our graph. So what we see here we see that the absolute minimum occurs at x equals 4. And the min value is the y-coordinate, is this value 3. So the absolute minimum, our function, the absolute minimum for our function occurs at our critical number, x equals 4, and the minimum value there is 3. Now, it is possible, though, so we did have to keep this endpoint in mind because it could be possible that this endpoint could have been further down along the y-axis. So if we had the endpoint down here, and it increased, and this was our sketch, well, then the absolute minimum would have occurred at the endpoint. So when we have these constraint problems where we have an inequality constraint like this, We also, not only do we have to look at the local maxes and mins that we find, like we did here, but we also have to look at the endpoints. And so what we can do to find the absolute min or absolute max is, if we have a sketch of the graph, we can just compare the values here. And the smallest value that we see, and we can also verify this on our sketch, is going to be the absolute min. Same thing for absolute max. Now, it looks like 30 would be the absolute max, but because of our sketch, we see that the function keeps going up and up and up. So x equal to 1 isn't an absolute max because there's this section of the graph that keeps getting higher and higher. So that's why we kind of need the sketch to help us identify if we do have an absolute max or an absolute min. And we can see that by drawing this in and knowing our intervals of increase-decrease. X equals 4 is definitely going to be the absolute minimum. And x, anything beyond, this section of the curve here, is eventually going to be higher than this other point. So the function just keeps getting bigger and bigger. So there is no absolute max on this one. All right, so that's going to do it for the preparation for this section. And where we're going to go with this, ultimately, is we're going to look at constraint problems where we're given a function that we're trying to find the maximum or the minimum for, but maybe instead of an inequality, we're given an equation. And we're going to see that next time. So we'll see you then. Bye-bye.